Hello, my name is Jan Scholtz. I'm from Cambridge University, and today I would like to talk to you about the look into the first galaxies and black holes with the JWST and specifically with the JADES survey. And I just would like to say this is on behalf of JADES survey. I'm just a small cog in it. So, um, at the beginning, we had the Big Bang, that's sort of 13.7 billion years ago. Then we had something called the recombination, and then eventually dark ages, where the dark ages were sort of before the first stars and before any galaxies. And then slowly you had the first stars in sort of within the first 50 million years after the Big Bang, and eventually first galaxies. And these first galaxies, that's what we call the cosmic noon. The cosmic morning, which is when actually the first galaxy and the first stars and actually started illuminating the entire universe. And before, we mostly use ground-based spectroscopy or alternatively ALMA array in order to study these. But if you really want to push into looking at these very distant galaxies and the first stars, you really need JWST for this because it's observing in infrared light, which I'm going to talk about later. And it's incredibly important to stress that JWST is currently the largest telescope in space. There is so far nothing bigger that can rival it, even close. And if you actually look into the comparison of this, JWST with its hexagonal mirror has a size of roughly 6.5 meter, but HST, which is something that it's replacing JWST's successor to Hubble Space Telescope, that one was roughly 2.4 meter. So more than the HST was already the main mirror was already larger than a person at 1.8 meters. So this is a huge increase in size. And because of this, we get much better resolution, so the sharpness of the images, but also much bigger collecting area. Now, this larger collecting area is allowing us to look into more distant stars and more distant galaxies. And this is this incredibly thing about universe is that light is essentially a time machine, because light has a limited speed. So the more distant things you look at, the more you look into the past. So, for example, the sun is roughly 8 minutes away from us by at the speed of light, which means that we always look at sun roughly 8 minutes ago. If you look at Mars, that's roughly a few hours ago. If you want to look at sort of the center of our galaxy, that's a couple thousand years ago. Closest galaxies can be even a couple million years ago. And if you detect the most distant galaxies and the first stars, you will essentially look at the universe as it was more than 13 billion years ago, and that is the true power of these large telescopes and looking into distant galaxies. So the first launch was on 25th of December, 2020. 2021. That was a very stressful Christmas day for everybody involved, but luckily things went absolutely perfect. The launch trajectory was absolutely perfect, which has consequences that I'm going to show later on. Very good consequences. And then the telescope was separated from the rocket, and we could actually start unfolding the telescope. So first they unfolded the solar array, then the communications antenna, so that we could actually communicate with the telescope, and then came the sun shield. So we need to keep the telescope as cold as possible, and because of this. There's this large sun shield that actually blocks any light coming from moon or Earth or even the sun, in order to keep it nice and cold. So that was extended this was something that it looks relatively small, but actually the essentially is the size of a tennis court. Then you start cooling, you start actually assembling the telescope itself. The mirrors started unfolding until you have a fully functioning telescope. And then there was this spectacular process of calibrating all of the instruments and doing the first images, where the people who, over the 6 months, who were involved, have done a spectacular job to preparing the telescope for science operations. So, because the telescope is optimizing for detecting infrared and detecting infrared, it's actually gold plated. The mirror is from gold. It's a beryllium mirror coated with gold. Usually on the ground for optical light, we use aluminum, but it's very bad for reflecting infrared light. So there we use gold. The sun shield is essentially, it's a multi-layer sun shield. So on the side of the sun shield, it's roughly so 50 degrees Celsius where the sun is shining, and on the other side in the shaded area, it's roughly minus 230 degrees Celsius. So you have more than 280 degrees Celsius difference across the sun shield in order to make the telescope as cool as possible, which is fascinating on its own. And the image quality improvement is beyond unbelievable. When you look at the WISE and the Spitzer, which are the previous infrared telescopes, and you compare it to the current one, you can just see this beautiful nebulae and the gas clouds compared to just little blobs and blobology that you saw in the previous telescopes, which were, I would like to point out, they were still amazing. But with all the technology, this is the leap in technology we are talking with JWST, and it's not just sharpness in images. It's also in terms of sensitivity. The sensitivity improvement is several orders of magnitude compared to the previous observatories. And for some wavelength range, this is the same as going from Galileo Galilei's telescope to a very large telescope, modern astronomical facility. It's the same leap. It's spectacular. And this is amazing advance in sensitivity and resolution allows us to sort of investigate the first galaxies. So this is something as a pre-JWST look. We thought that as you go further and further to younger and younger universe, that the galaxies should start behaving more chaotic. Because it takes a while to develop a nicely rotating disky galaxy. So you can see, so on the left, a very nice spiral, and then as you go further and further, kind of you see these blobs and this sort of messy systems. But actually, when we look into the first images, and you can look at it visually, you don't have to do much of a scientific analysis. You just get these beautiful spirals, these beautiful evolved galaxies. This is one of the deepest observations currently with JWST. This is from the JADES survey, and every single point that you see in that image is a galaxy, and they are beautiful. They are spectacular. When you even compare it to just sort of ground-based, right, where before there was just sort of 4 or 5 little galaxies in a small region where we saw it, and now when we look at it with JWST, suddenly we realize that this sort of a little tiny cluster or overdensity of galaxies that wasn't even everything within the overdensity. There are tons of more galaxies there. That's performing this little dance. There are some where we saw them as like little red blobs, and now we see them as these beautiful spiral galaxies. On some of them, we just didn't see them in the first place, right? So they are just completely new discoveries for us. The same thing goes with Hubble's. When you compare Hubble Space Telescope and JWST, what before was sort of a mess now is a beautiful spiral galaxy as well. So That is spectacular. And then finally, when you look into, you actually start to see that there are a lot of sort of evolved major spiral galaxies seen by JWST, and we see way more of them and way earlier. But the thing is that the strength of JWST is not just looking at images, it has a spectrograph. So with spectrograph, you can look at it that, first of all, you can start with simple three-color image, your blue, green, and red. You can sort of look at their brightness, you'll see something. And then you'll kind of start looking into filling the differences between the gaps between the different colors. You will start increasing them with more and more filters, and you will get more and more colors. However, at some point you realize that's actually really an efficient way of doing this with just more and more filters, because you want to keep dissecting the light, because every single time you dissect the light to a little bit smaller smaller color, it actually gives you more information. So you can start using, for example, prisms, where you shine light through a glass prism, and you get the rainbow, and in the rainbow you can have tons of information. Or alternatively, you can use something called a grating, which is sort of a different prism, and essentially what you get is this sort of incredibly you will get the rainbow, the incredibly finely dissected sort of colors. And that's incredibly important, because all of these peaks that you see in that's actually a transition from emission line from some sort of element, whether it's oxygen, hydrogen, neon, carbon, or whatever. And actually, they can tell you tons about the sort of chemical composition of the galaxies and of the stellar population, and etc. And one other thing is that we need to start looking at infrared, because we are looking at galaxies so far away that the universe has actually expanded a significant amount between then and now, which means that also the light that they emitted, for example, in UV or optical wavelengths, has been essentially stretched in due to cosmological expansion, all the way to the longer and longer wavelengths, until they ended up in infrared, into much longer wavelengths. And this is what we call the cosmological redshift. This is something that's how we measure the distances of galaxies, and also their ages. And I would just like to give you two examples of the most distant galaxies or black holes that we discovered with JADES. So one of them is something called the GSZ14, and you can see sort of the field how we discover it. And among the field, we also you can also see a sort of the image. It's actually right next to a foreground galaxy. There's this sort of a blue part in that little span, and it's only the red one, the smaller one, the red one, that's actually our galaxy. This one is at redshift 14, and the reason why we know it is because we got a spectrum from it. So we dissected all the different colors, and within that we actually found that there's a sort of a rising continuum until there's a very sharp break, which we call the Lyman alpha break. And it's essentially, the break is caused by neutral hydrogen that actually absorbs all of the light that is bluer, shorter wavelength, or bluer, than the Lyman alpha break. And that is supposed to be at exactly one wavelength. It's 1215 angstroms, or 0.12 microns. So if we know where we actually detected on the spectrum and where it was supposed to be, we can calculate the redshift, sort of how much it has shifted, how much the universe has expanded, and based on that we know the distance, and we also know the age. So this is something that is less than 300 million years, roughly 280 million years after the Big Bang, which is sort of, we're talking about 13.4 billion years ago. Now, GSF14 it's quite massive, actually. It's like 830 million times the mass of the sun, and it's roughly 820 light years ahead. But it's still, when you look at it compared to our Milky Way, which is over 1 trillion times the mass of the sun and 100 light years across, is that this thing is just an embryo of a galaxy that one day is going to become our galaxy. We see the embryos of our own galaxy at this point. This galaxy will have to grow by almost factor of thousands in size. And then also more than a factor of thousand, probably more in mass before we actually reaches what we call a galaxy today. The other one that I would like to talk to you about is GNZ11. So what's spectacular about it is that this is the most distant galaxy detected and observed by Hubble. And it was always a puzzle to the astronomers because it was incredibly bright compared to what we would expect. So this is a JWST image of it. It's sort of the orange blob in the middle. What if you wonder what is that red galaxy in the top left? That's just a foreground galaxy. It's significantly closer to us. It just happens to be there by chance. And I just wanted to show you this HST spectrum of GNZ11, which is something that was done by Pascal Esch with incredibly effort by HST to get this spectrum, and therefore they also saw the very sharp drop, the very sharp break, and they realized that this is roughly a redshift 11, hence GNZ11. And the JADES collaboration could not wait to actually see the spectrum. And we got a spectrum of it. And this is what we got with JWST. So completely different sort of quality. Look at the beautiful sharp break. Look at all of those peaks, which are actually all of the emission lines from nitrogen, carbon, neon, oxygen, that just show you. And actually, when you do a deep dive into all of these emission lines, what you actually find out is that this thing hosts a supermassive black hole, a very active supermassive black hole. And the material that's infalling into the supermassive black hole is shining a huge amount of harsh radiation that's causing some of this emission lines, and also it's causing this incredible brightness that we before didn't really expect. Also, it has a very complex what we call morphology or shape. So it has a sort of a point source in the middle with a disky galaxy underneath, and then there's this haze, this sort of like an extended structure that we don't really know what it is. But when you look even in further, you actually realize that there are tons and tons of galaxies around. So on the left, you see an image of in the blue, of couple of sort of like other galaxies that we saw around it. The orange are just foregrounds, contaminants. But when you look at the image on the right, and then you see little numbers across all of on the image, and what you find out is that there are just tons and tons of galaxies all around it, and the same what we suspect is the same distance as GNZ11, which would indicate that it's essentially in something called a protocluster, or this like a very early density, the over density that will one day become a cluster of galaxies. And this is something that has been happening 400 million years after the Big Bang. So there's this incredibly fast growth of structure in the universe. So in summary, within the first 2 years of JWST operations, we already broke the record for the most distant galaxy twice. There's one called GSZ13. I didn't even talk about that one. Then we have GSZ14. The JWST discovered the most distant black hole. And we find that just galaxies evolved way faster than we thought before the launch of JWST. And we see evolved galaxies with evolved black holes less than 500, 600 million years after the Big Bang. And that's just incredible. Nobody thought that the universe was going to evolve so quickly. I cannot wait to what's going to happen for the next 20 years of scientific operations of JWST. Thank you very much, and let me know if you have any questions.